Okay, so in the last video we had just defined a function, and so maybe I need to be more clear about the immediate goal. So the immediate goal for us right now is to extend our definition of cardinality to infinite sets. So right now we have a definition of the size of a set, or more formally, the cardinality of a set. That is, if we have a finite set, then the cardinality is simply the number of things inside of it. So if we have a set with 5 elements, the cardinality of the set is 5. We'd like to extend a notion of size. We'd like to figure out kind of what the natural notion of size should be, I should say, for sets that aren't finite, for sets that are infinite. And that's our goal right now. And towards that goal, we've been taking a more formal look at what a function is. So just to review the last video, any subset can be thought of as a relation. So I can always kind of, it's more or less a property that's, I pick a set, and then I pick a property regarding that set, and then everything that satisfies that property, is kind of related in that sense. And so that's kind of how I think about relations. Of particular importance to us right now is the case of relations as on the products of sets. So relations on the Cartesian product A cross B. And in particular, we're interested in the special case of this in which R can be thought of as a function. So a function is a special kind of relation. It's a relation in the sense that it's a subset of the product of two sets, A and B. But it's a function. We can think of it as a function. And by that, I mean we can think of it as like a mapping or like an input-output, in which I can basically plug in anything I want. That's what I mean by this. The domain of F is A. So anything that's in the supposed left entry, I can plug it in and get something. And then also the more important distinction is that I only get one thing out. The function outputs something, a deterministic thing that comes out of it. So the way to formalize that is to say that if xy and xz are both elements of the function being the set, then the second entries have to be the same. And so just an example down here, the unit circle in R2 cannot be thought of as a function. Why? Because, well, we've got 2 points on the unit circle, these two in particular, 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. These have the matching second entries. These have second entries that don't match, but matching first entries, right? So, if I want to think about the circle as a function, I'm sort of out of luck, because then I have to ask the question, well, what should the function output at 1 over root 2? Should it be this or should it be this? And I'm not sure. And so because of that, I can't really think of this as a function. So the next thing we should do is define an inverses. And you can define the inverse of any relation. But I'm gonna stick to functions. So maybe I'll type this out. So note that with functions, as well as relations, but we're mostly interested in functions with regard to this, we can always define inverses. How should we define inverses of functions? Thinking about them as a set, I tend to think that the definition of the inverse of a function, thinking about the function as simply a relation as a set, is actually much simpler to look at and makes a lot more intuitive sense than the actual definition you see in like a pre-calculus class. So if f is a mapping from A to B, that's what this means. F is a function from A to B. Define f inverse to equal the set of all y comma x such that xy is an element of f. So basically just take every entry and flip it. Entries. Note this is always a set, but it's not necessarily a function. So let me go ahead and say that. Clearly, this is always a relation on B cross A. And note it is in B cross A, not A cross B anymore, because we've, the y's are from B and the x's are from, if xy is in F, then x is in A and y is in B. And so, and then now the second entry is the thing from A, and the first entry is the thing from B. So we have a relation on B cross A, but it's not clearly always a function. So just as an example, let's look at the function, a function people are probably pretty familiar with. It's a function from R to R. And it's what we typically would write f of x equals x squared. Now we're thinking about functions as sets, so really, as a set, we can think of this as basically the set of all x squared, really, such that x is a real number. So that's as a function what f is. It's just the set of all pairs x squared, such that x is a real number. So this is a function. This is definitely a function. But let's think about f inverse. F inverse in that case is going to be just the set of all x squared x, obviously, such that x is an R. That's just blindly going from the definition. Just flip everything. Now, is this a function? And by the way, this does line up with with what you typically think of as the inverse of a function, because if xy is in f inverse, then what has to be true? Well, it has to be that x is the square of y. Or in other words, then x has to equal y squared, right? Y has to be something that you square it and get x. Implies that y is equal to the plus or minus the square root of x. So this is not a function, right? Because it's not clear. If I plug in an x, what should y be? Should it be positive the square root of x, or should it be negative the square root of x? This is not a function. So this example kind of confirms that, inverse is defined this way, in the simplistic way, just by flipping everything in the x-coordinate with everything in the y-coordinate. It does line up with what you typically think of as the inverse of a function. And it also confirms that when you do this, you don't necessarily always end up with a function. It also becomes clear, visually, kind of, at least with respect to the real numbers, like what's going on here, right? So what does x squared look like? It looks like this. Let me try again. This is what x squared looks like, where this is the y-axis and this is the x-axis. Now, what am I actually doing here? I'm just plotting all of the points on the relation f. This is just everything in f. And if I'm flipping all of the y and x coordinates, then what I'm really doing here is doing this. I'm just kind of making the x-axis the y-axis and making the y-axis the x-axis. So this is f. And then what I get by taking kind of the inverse is I get this set. If I kind of just flip this with this, it's sort of as if I kind of mirror it in this way. I get the same picture, but looked at from a different angle, in which you have an x, in which the upper axis is the x-axis and the horizontal one is the y. And you can see that this is no longer a function. It doesn't pass the vertical line test, right? If I've got an issue here, because, well, we have to think about it. So this is f inverse. So what I want to identify is, for f inverse to be a function, what else is needed about f? Well, let's look at the let's try to identify the particular problem with x squared. The problem with f of x squared is information loss. What do I mean by that? Well, what I mean by that is that suppose that x squared equals 4. Suppose I tell you that x squared is equal to 4. In other words, f of x is equal to 4. What is x? Right, so I've looked at f of x. I've told you that it's 4, and my question is, how do you go in reverse? There's information loss if you can't go in reverse, and you can't here. It's impossible to tell me with perfect accuracy what x was if f of x equals 4 for the function f of x equals x squared, because it could have been 2 or negative 2. No way to know for sure. And so how does information loss, how does this observation that we just made about information loss necessitate that the function f inverse is not a function? Well, let's just note. So let's say, why is this a problem? Well, let's just note that if negative 2 squared is equal to 4 is equal to negative 2, positive 2 squared, well, then what that means is that 2, 4 and negative 2, 4 are both elements of f. And so these are two elements of f, and when we flip that, then we end up with the fact that 4, 2 and 4 minus 2 are both elements of f inverse. And that's a problem. Now, because I flipped them, the lack of information has turned into a lack of determination of what f should do when I plug in 4. That's the problem. So there is a one-to-one kind of correspondence between non-invertibility of a function, and when I say that, I really mean you can always kind of take this inverse in the sense that I described it, but is the inverse a function? It really corresponds to whether or not the function suffers from information loss. So, and this probably is still a little bit murky, so there's another way to visualize functions. Let's think about a more general way to visualize functions. Right? Functions from R to R I can graph in this way. Functions from the real numbers to the real numbers I can graph this way, and this is the way that you're used to graphing a function. But what if it's a function from, a set of all types of bread to apples? It's not not all types of objects are going to be able to be visualized that way. So a general way to visualize functions is as mappings. Basically, here if f maps a to b, if f is a function from a to b, then basically it's exactly what it looks like. It's a set of instructions on how to map points in A to points in B. And I can draw that by just kind of drawing the sets. So here's the set A. And then here's the set B. And then basically for any point in here, f is going to map that to a specific point in here. This is the function f. It's a mapping. It maps all the stuff in A to stuff in B. Doesn't have to be everything in B, just stuff. And there's a lot that becomes this is a very simple kind of picture to draw, but there's a lot that it's precisely because this is a simple picture to draw that a lot of things become very clear very quickly. For example, when I was reviewing what I did in the last video, I noticed that I might have confused some people with respect to the difference between the domain and the codomain. Well, what's this picture kind of tell me in general? Well, the codomain is just B. That's just the definition. If I put a B here, then that's by definition the codomain. The range, remember, the range of f is equal to the set of all y coordinates. Oh my God. I just take them all. And so, what does that look like in this picture? Well, here's my set A, and then here's my set B, and then, if I take all the y coordinates, I get some subset. This is all the stuff that something in A maps to. Everything in A gets sent inside here, and nothing gets sent outside of here. Everything gets mapped inside here. This blob, this subset, is the range. And this is the codomain. And you can see very clearly now what the difference between the range and the codomain is. Now, how does this help us in kind of visualizing inverses? Well, what's defining for a function? So if I were to draw another line coming up from x, like this, that would not be a function. So this is not a function. It's no longer deterministic. It's not clear where f maps. Now, let's think about what it looks like for information loss to exist. Or rather, let's think about to take f inverse in this picture is simply to reverse all the arrows. So this is clearly not a function. However, let's draw a function that is a function but still has information loss. A function with information loss looks like this. We've got a set A, we've got another set B, and then there's one particular point, well, actually two particular points. It's a function that maps to the same thing. So there's this particular z, and there's this and then there's two points x and y and a that aren't the same, that both map to the same point z. So this is clearly a function because there's nothing unclear about where to send x and y. But when I reverse the arrows, I lose determinism. And I think you can kind of see it very clearly just from the picture now, kind of what the condition that we need in order to have an inverse of a function is. So let's draw real fast. The picture for a function which is invertible. So this is a function f which is not invertible. Because when I reverse the arrows here, I no longer have a function. But the picture that for is invertible looks like this. So here's A and here's B. And then let's just say these points here are everything in A. What it would mean for this function to be invertible is that all of these arrows need to go to a unique thing. So this arrow, if this arrow goes here, then none of the other arrows can go to that point that I just mapped to. This has to go to something unique. This has to go to something unique. Whoops. And this has to go to something unique as well. And notice nothing maps here, but that's okay. That doesn't matter. The point is that all the arrows go to something different. And so there's kind of a one-to-one correspondence then at that point between this. There's kind of a one-to-one correspondence between this point and this point, whereas that's not the case here. I can't identify necessarily z as the same thing as x because it's unclear whether I should identify it as y. Whereas here you kind of have a correspondence. There's no loss of information by putting the arrow and making the arrows two-sided on all of these. I'm just kind of identifying, this point goes to this point goes to this point goes to this point, etc. And that kind of motivates the definition which I'm about to write, which is called one-to-oneness. The function being one-to-one is a function that looks like this. So here's a definition. A function f mapping a to b is 1 to 1. Another way to say that is injective. If either f of x equals z, and if I meant to say whenever, not either. Whenever it's the case that f of x equals z and and f of y equals z, then x equals y. In other words, if 2 points map to the same point, then they have to be, those 2 points that both map to it have to be the same. Maybe a more clear way to say it, so another equivalent way to say it. Equivalently, whenever x is not equal to y, f of x is not equal to f of y. This statement here is actually the contrapositive of the statement here, and I'll define what contrapositive means when we get to the logic stuff, but these are equivalent. And a fact that's probably obvious at this point that we've sort of justified. A function f, well, let me start it like this. For a function f, f inverse is itself a function if and only if, that's what this if with 2f means, if and only if, which means this, yeah, I'll say that in a second, is itself a function if and only if f is 1-to-1. What I mean by if and only if is that if f inverse is a function, then f had to be 1-to-1, and if f is 1-to-1, then f inverse has to be a function. It's a two-way street. This can go to this can go to this. That's what if and only if means. So how does this relate to cardinality? How does this actually help us in thinking about, in a more mature way, the size of a set? Well, let's think about an example. Let's do a quick example of an injective function. Let a equal a, b, c, d, and then let b equal 1, 2, 3, 4, 5. And then here's the set A, and then here's the set B. Let me draw the points out. Here's A, B, C, D, E. And then here's, wait, I don't have an E. Excuse me. Put D down here. And then here's 1, 2, 3, 4, 5. Now, let's define an injective function. Let's say C. Let's take C and map it to 5. Let's let D get mapped to 3. Let's let B get mapped to 2. And let's let A get mapped to 1. So, you know, this does define a function. This set of arrows I drew defines a function. I'm basically saying f of A equals 1, f of B equals 2, f of C equals 5, f of D equals 3. And, you know, also another way to say it would be to say f is equal to the set, you know, A1, B2, C5, D3. So that's just some review kind of functions, thinking about them in the various ways that we have to think about them at this point. But the thing to notice is that, note that the cardinality of A is smaller than B. And that means something here. That matters to some extent. It means that I can define an injective function from A to B because I can always find a unique thing to map to. However, I'm always going to miss a point. Any function I define from A to B is going to have to miss a point. It's going to have to miss a point because B is fundamentally bigger. This kind of identifies, so in this case, the existence of an injective function here. So what's the significance here? I can only define an injective function or a one-to-one function from a to b if a is smaller than b. If a was bigger than b, I couldn't do this. If a was bigger than b, like if I took away 2 of these points, then there would be nothing for at least one of these points to map to. I could map 3 of these guys to 3 of these guys, but then I would be out of points because a is bigger. So the existence of an injective function is sort of something that identifies that the domain set is actually smaller than the codomain set. And that's actually where the word injective comes from. The word injective comes from this fact that what I'm sort of doing is I'm sort of injecting the set A into the set B. I'm kind of coming up with some associations between points in A and points with B, and I'm kind of taking this whole set, and then here's the set B, and then here's some subset of B. I'm sort of taking A and I'm like embedding it into this. I'm injecting or embedding the set A into the set B. By coming up with this kind of mapping, I've sort of have this one-to-one association with A in 1 and B in 2, and I've sort of kind of, through that association, sort of projected A inside of the set B. I've injected it into there, and that's why it's called an injective function. It does an injection. It injects A into B. So that's kind of step 1. We've got a definition sort of less than or equal to. So now let's think about like another property of function. So we know in general that the range of B, or range of f, I should say, is not equal to the codomain of a function f. Right, and you can see that very clearly in this picture. This right here is range, and this right here is codomain. But what if it is? If it is, what does that mean? If it is, then everything in B is, in some sense, covered by something in A. What I mean by that is that everything in the codomain has something that maps to it. Let's draw that picture. So let's draw what that looks like. So here's my set A. I'll draw like 4 points. Actually, I'll draw 5 points. And then here's my set B. And I'll draw like 4 points. Right, so here's a function f that maps to all of B, right? Everything. Oh my God. Everything in B gets mapped to. So it's covered, right? So that's kind of what that means. It's a covering. And just kind of like the fact that if I have an injective function, it sort of implies that A has to be in some sense smaller, or at least the same size, because otherwise, otherwise something would have to, otherwise there'd have to be a point in common by the kind of the pigeonhole principle. This is kind of the opposite thing. I can only do this if B is smaller than A. I can only cover B like this if B is at least is smaller or greater than A. So let's go ahead and make that a definition. So here's a second definition. A function f from A to B is onto or surjective if the range of f is just equal to b, all of it. Equivalently, for any y and b, there exists an x in A such that f of x is equal to y. So every y has something that maps to it. That's what I'm saying. So, just to give you an example of a function from the reals to the reals that is surjective but not necessarily injective. Oh, and by the way, wait, I didn't define a function up here. I can do this. So this function here, I have two points here that map to the same place. So it's not one-to-one, but it is onto. So it's not one-to-one, but it is onto. An example of a function from the reals to the reals that's one-to-one, but not, onto, but not one-to-one would be something like this. Right? This is also onto, but not one-to-one. Right? Everything, I have the entire vertical axis. Everything on the vertical axis has something that I can plug in that will get that. But this guy right here, let's say, also has a point right here that I have two x's that kind of map to the same thing. So not one-to-one because of this, but it is onto because I get the whole vertical line, the whole vertical axis. And so let me just summarize in terms of what we actually care about with respect to functions right now, the key takeaways from what I've said so far. So just as a function can only be injective if A is smaller than B, or at least no bigger, a function can only be surjective if A is bigger, or at least no smaller than B. This is the key takeaway. And so what would it really mean for two sets to be the same size? Well, it would mean that you have both of these at the same time. Thus, f can only be injective, can only be both injective and surjective if A and B are the same size. And so now we have a criteria for same sizeness that can potentially apply to infinite sets. I have two sets that are the same size if I can find a bijection between them. And that what I mean by bijection is a function that's both injective and surjective. So here's the final definition we need to define cardinality. A function f from A to B is called a one-to-one correspondence or more commonly a bijection if it is both injective and surjective. So now we can potentially define cardinality without talking about directly the number of things in the set, meaning that I can come up with a definition of size of the set that doesn't actually explicitly count everything. So we can use this. We state the mostly actual. Well, we state. Okay, let me say it like this. We state we're going to extend this is going to extend our definition of cardinality to infinite sets, but it's not going to be the full definition just yet. Well, okay. So using this, we can extend our definition of cardinality. So let's do that. So here's the definition. First of all, recall that the natural numbers are like this. There's an ongoing controversy in the mathematical community about whether the natural numbers include 0 or not. My personal political stance on whether it should be included is that I don't care, and it should be included when it's convenient to include it, and only then. I guess honestly, like the technically correct definition, I think that the natural numbers should include 0, but it's who cares? This is stupid. But anyway, that's the natural numbers, and so I'm going to use this and the definition of bijection to finally define cardinality in the mature way. So here's the definition. We say that for a set A, we say, for a set A, I'll put bars around A, is called cardinality. So first of all, I'm going to redefine what it means to call the cardinality of A equal to n. So we say that the cardinality of A equals n if, the old definition of this is that it's just counting the number of elements. If there exists a bijection which maps F, which maps this set 1, 2, 3, ... up to n to A. So if I can come up with a bijection that maps the set of 1 through n up to A, that's my new definition of what the cardinality of A is. So that actually does match up with our original definition, because there's only a bijection, if there's the same size. So this does work. We say that A, but now I can kind of go further. We say that the cardinality of A is equal to omega, or sometimes you use the Greek letter aleph. I'm going to try to draw it. Aleph not. This is a Hebrew letter. But they're both correct, I think. I don't know. Some people would say this is incorrect, I think, but I think it's perfectly correct. So we say that the cardinality of A is omega if there is a bijection F which maps the natural numbers as a whole to A. So this means that A is an infinite set, and it's in some sense the same size as the set of all the natural numbers. So if A is equal to omega, and I'm typically going to use the letter omega instead of this aleph symbol because it's easier to write. If the cardinality of A is equal to omega, we say A is countable. Countably infinite. This is the type of infinity that we're going to refer to as countably infinite. In either case, we say A is countable. And then finally, if A is equal to n for some n in n, the natural numbers, we say A is finite. So finite sets and countably infinite sets are both countable. But so this word countable is just kind of like a catch-all for finite sets and countably infinite sets, which makes sense. We can count them in either way. And by the way, and finally the function f, the bijection, the function f in either case is called an enumeration of A. So that's all the formal kind of words and definitions. Let's just kind of confirm real fast and observe that this is an extension of our old definition of countable. So, if A is equal to A, B, C, D, then, this function, I can just draw the picture. Here's A, B, C, D. I can map the set, really I should put over here. I'll put it over here. 1, 2, 3, 4. Here's the bijection. Map 1 to A, of course. Map 2 to B. Map 3 to C. And map 4 to D. Right? This is a bijection F, which maps 1, 2, 3, 4 to A. Thus, the cardinality of A is equal to 4. So that does match up. So this is just an extension to infinite sets. We still haven't extended it to maybe all infinite sets. It's unclear if all sets are countable right now. But we have extended it to a certain class of infinite sets. And so, what I mean by enumeration, this concept of an enumeration is going to be really important to computability theory. So fundamentally, all it really is, an enumeration. Oh my God. An enumeration of a set is just a comprehensive way to list out the elements of A one at a time. And so we'll show some examples next time. So I think I'm going to cut it here, and then in the next video we'll begin to do some examples and show that various sets are countable and begin to work our way up to some important results regarding the countability of certain sets of interest.